film number 4 in this series is about filters. And the filters in this demonstration is they are both based on the inverting amplifier. So we have to keep in mind the expression for the gain for inverting amplifiers. The A is minus R2 over R1. The first amplifier, the first filter, is the so-called low-pass filter. A low-pass filter has a frequency response like as shown in this graph here. And this is actually a frequency plot of the gain. So you have the frequency here. Actually, the frequency is, in this case, angular frequency, radians per second. And then you have the amplification here on the y-axis. Actually, the gain is in decibels, but that's not a big point here. The thing is that for low-pass filters, you have a controlled gain for low frequencies, for example, bass signal, and then you cut away the high frequencies, for example, the treble, bass og diskant på norsk. Now, this is called the pass band, and this is called the cutoff band. So you cut away something and you let something pass. So if you send us a normal audio signal through this filter, the bass will be kept and the treble will be cut off. The cutoff frequency, where it all starts to either pass or cut off, is defined by the components R2 and C2. So that is the cutoff frequencies. What happens here is that we have a basic inverting amplifier like this. If I were to remove C2, you can see that it's a basic inverting amplifier with R1 and R2 connected to the negative terminal of the op-amp, just like the one that we had here. R2, R1 connected to the negative terminal. But we now have a capacitor as well. And remember, for low frequencies, the capacitors are to be considered as open circuits, that there will be no current through it. So the current that comes here will not go through C1, it will all go up through R1. So for low frequencies, the capacitive reactance is more or less infinite, and therefore the impedance in this part here is basically infinity in parallel with a real value R2, which is basically R2. So for low frequencies, the amplification is as for the normal inverting amplifier. For high frequencies, on the other hand, the capacitor becomes a short circuit more or less. So the current that comes up here will go through, everything will go through C2 and nothing through R2, because C2 becomes a short circuit. And therefore, at high frequencies, the capacitive reactance becomes 0. The impedance is something in parallel with 0, which is 0. And the overall gain is 0 over R1, which is 0. And it's a so-called signal killer. So it will kill the high frequencies. So that was the low-pass filter. Remember, resistor and capacitor in parallel, where we usually had R2 alone with an inverting amplifier. High-pass filter has the opposite graph here. You have the cutoff region here and the pass band at high frequencies. So this will keep treble and cut away the bass of the of the signal if it was audio. The same thing, the cutoff frequency is now decided by these two components, R1 and C1. And for low frequencies, remember, low frequencies, this one becomes an open circuit. The capacitive reactance is more or less infinity for low frequencies, thus an open circuit. The impedance overall is the sum of the two, because they are connected in series, and the impedance becomes infinity. The gain, R2 over Z1, this one over this one, is R2 over infinity, which is 0. So you have a signal killer for low frequencies. For high frequencies, the capacitance, the capacitive reactance, that one becomes 0. So it's more or less like if we short circuited the capacitor there, like this. It's more or less like if it wasn't there. So therefore, the overall impedance becomes R1 for this section here, and the overall gain becomes minus R2 over R1, which is a normal amplifier. So for high frequencies, we have a normal amplifier. For low frequencies, we have a signal killer.